So in this video, we're going to take a look at an example where we get to use our new theorems to optimize a particular real life scenario. And in this case, the setup goes like this. We have this function here, g of x equals 1 over 50 times the quantity in parentheses, 200 over x plus x over 15. And here x represents the speed of a bus in miles per hour. And the g represents the rate at which the bus burns fuel, represented in gallons per mile. And if fuel costs $3 per gallon, find the speed that will produce the minimum total cost for the 250-mile round trip. Feels like a lot of things. And it is. We're going to put all this together. And then once we get the function put together, then we're just back to our regular optimization processes and finding the minimum total cost. So we have to think here about a function that relates speed, which, in miles per hour, which is what x is, to total cost. Right now, what we have is a function that relates the rate of fuel burn to the miles per hour, which is great, but that doesn't tell us anything about total cost. So to get total cost, we have to kind of think this through a little bit. So we want cost in terms of miles per hour, where this is the miles per hour, and this is total cost in dollars. So what we're going to do here, we're going to take this function that we're starting with, this one here, and then we know that fuel costs $3 per gallon, but this function represents gallons per mile. So we also need to factor in that we're going 250 miles. So we're going to take our rate at which the bus burns fuel, we're going to multiply it by the 250 miles. That will give us the total number of gallons needed. And then to get the total cost, we'll have to multiply that by 3, since the assumption here is that fuel costs $3 a gallon. So what that's going to ultimately look like, we'll clean this up in a minute, but we're going to have 3 times 250 times our original function that we started with, 1 over 50 times the quantity, 200 over x plus x over 15. That's actually going to give us the total cost based on the miles per hour that we were traveling. Okay. Now, the whole first part of this is just going to be us cleaning up this expression, and then we'll start to optimize it to look at how do we minimize cost? How fast should we be going on average? And then what is that minimum total cost? Okay. So looking at all of this, these first three, the number 3, the 250, and the 1 over 50, those are all just constants. So I can multiply those together just to find out what does that number come out to be. And so when we do that, we get 3 times 250 is 750. We divide that by 50 or multiply it by 1 over 50, depending on how you want to look at it. And we get 15. And then we have the 200 over x plus x over 15. And I'm actually going to distribute this through. Okay. So 15 times 200 is 3,000 over x plus x. Or if you want to look at it this way, 3,000 x to the negative 1 plus x. So there is our cost function. Gives us total cost in dollars when we know the miles per hour of the vehicle. Okay, now we want to know, find the speed that's going to produce the minimum total cost for the trip. Well, we now have the extreme value theorem and the critical point theorem that tell us how to find absolute extrema. The extreme value theorem tells us how to find absolute extrema on a closed interval, and the critical point theorem tells us how to find absolute extrema regardless of what kind of interval we're dealing with. Now, I'm going to make an assumption here. The assumption that I'm going to make is that the minimum miles per hour that the vehicle could travel is 0. That would represent a stationary vehicle. And we certainly could include that. Oh, sorry. Actually, no, we can't include that. I was just thinking theoretically, but you'll notice if we actually tried to put 0 in, we'd have 3,000 over 0 as our first term. So in fact, we are looking at an open interval starting at 0. And then let's also make the assumption that we have a maximum amount of miles per hour that we could be traveling. And I'm pretty sure, I don't actually know what the maximum miles per hour in the US is. I know around here locally, usually on the freeway, we can only go up to about 70, but I have been places in the country where 80 was the max speed. So I am going to make the assumption that you can go up to and including 80. Now notice that this interval is neither open nor closed. It has one end that's open and it has another end that's closed. So we're hoping that we can use our critical point theorem here. But the key with the critical point theorem is that this has only one extreme value, only one max or min in that interval, right? That is what our critical point theorem said. It had to have exactly one critical number in that interval. So let's see. Let's find a critical number, which, remember, to find our critical number, we have to start by taking the derivative. So here, the derivative of 3,000x to the negative 1 is negative 3,000x to the negative 2. And then the derivative of the second term, x, that's just 1, right? So then we have plus 1. And again, we're looking at 0 to 80. Okay, continuing with our process for finding a critical point, we're going to set this equal to 0 and solve for x. Whoops. Going to subtract 1 from both sides. Negative 1 equals negative 3,000 x to the negative 2. Or again, you could think of this, if you prefer, as negative 3,000 over x squared. Okay. So now we'll multiply both sides by x squared. So we have negative x squared equals negative 3,000. Divide both sides by negative 1. X squared is equal to positive 3,000. And then we need to square root both sides. And again, technically this gets a plus or minus, but we're going to be ignoring the negative values because we can't realistically go negative miles per hour, right? So if I take the square root of 3,000, that gives us approximately 54.77. So we do, in fact, have a case where within this interval, there is only one critical point. And so by the critical point theorem, that says that if this thing ends up being a local min, then it's also the absolute min. Okay, and that's what we're trying to find. What is the absolute minimum, right, total cost? So now we need to check the second derivative to see what the sign of the second derivative is when x is about 54.77. Okay, so c double prime, c prime prime of x equals, when we go back here, again, we're going to take the derivative, we're going to go the first derivative, bring the negative 2 down front as a multiplier. So now we're looking at positive 6,000 x to the negative 3, and the plus 1 is going to go away. So 6,000 x to the negative 3. We're going to put in that, what was it, 54.77 approximately. So we're going to do c prime, let's just call it 55, right? Because 54.77 is 55. 6,055 to the negative 3. We're going to plug that into the calculator. So we have 6,000 times 55 to the negative 3. And that comes out to be about 0.036. But remember, all we care about is the sign. So again, this tells us that at this value of 55, our second derivative has an upward cup shape, which means that that 55 is a minimum. And specifically by the critical point theorem, it is an absolute minimum within that interval. So how fast do we need to go to minimize our total cost? We need to go 55 miles per hour. We could then, if we wanted to actually find the total cost that that represents, we could go back to our total cost function over here and plug in, well, actually, when we simplified it, it was it was this, right? There's the simplified version. If we plug the 55 into that, that'll actually tell us what the total cost would be. And so just out of curiosity, I'm going to do that real quick. So 3,000 times 55 to the negative 1 plus 55. So we're looking at a total cost of $109. Total cost 109.55.